Welcome to this video on annuities and loans. In this video, we are going to develop the formulas and thinking for annuities and loans and solve scenarios. In a previous video, we looked at the math that helped us answer questions about accumulating money. In this video, we're going to be focusing on the math and the financing questions when we're withdrawing money from a retirement account. It turns out that the way withdrawing money from a retirement account works the same way that loans work. And we can think of a loan as the lender depositing money, a lump sum, into an account and then getting withdrawals from it. The withdrawals from that lump sum is coming from the person who borrowed the money. So you can think of a loan as an annuity for the lender. The formulas for finding the present value of an annuity or a loan is given here, and these formulas look similar to the formulas when we're talking about accumulating money. But instead of having future value, when we're accumulating money, we're talking about the future value, we're going to be looking at present value. So future value is still future value, present value is PV. Our I, just like when we were accumulating money, is going to be our R divided by M. T is time in years, R is annual interest rate, M is the number of times per year that we're compounding, and our N is our total number of payments or our total compounding periods. Just as when we were accumulating money, it's important that our style of compounding matches our frequency of deposits. If we want to solve this formula here for payment, we have this. A couple things to notice here is in the previous formula, when we were accumulating money, the 1 plus I was first in the fraction and the exponent on our N was positive. Now it's negative. So watch out for that. We talked before in a previous video about the accumulation side of retirement scenarios. So when we're saving up money, we're taking money each month and we're putting it into an account, building up this big pile of money. This is our saving for retirement side. The money that we're putting into our account each month, that's our payment. We typically start out with a present value of 0, and we're trying to find what is the future value. So how big is this pile of money after we've saved for 20 years or whatever. When we're talking about annuities or retiring and pulling money out each side, we're solving this side of this scenario. So we're no longer building our pile of cash, we're pulling money off our pile of cash. So we're pulling money out of our account each month. No longer putting in, this time we're taking it out. Frequently, but not always, we're ending up with nothing in our account. So that means our future value was 0. This amount that we're pulling out of our account, that's our payment. And the present value is how much is in the account when we retire. The thing that happens is the future value of the accumulation side ends up equaling the present value of the withdrawal side. The first thing I always do when I'm doing one of these retirement scenario problems, I think about which side am I on? Am I on the withdrawal side or am I on the accumulation side? Or maybe I'm doing a problem that uses both sides. And if I am, I have to use this idea that the future value of the accumulation side is going to be the present value of the withdrawal side. Let's look at a specific example. When Alonzo retires, he has $750,000 in his retirement account that earns 7% compounding monthly. If he wants the money to be paid out over a period of 30 years, how much can he withdraw each month? Thinking about which side we're on, we know that Alonzo has $750,000 in his account and he's withdrawing money each month. So that means we're on this withdrawal side. Thinking about what our given information is and what our goal is, My given information is I know that he has $750,000 in his account right now. So right now he has a present value of $750,000. If we're on this side of the retirement scenario, we're withdrawing money each time, it's always going to be a present value that we have a large sum in and not a future value. Our account earns 7% compounded monthly, so my R is 0.07, my M is 12. We want the money to be paid out over a period of 30 years, so my T is 30. How much can he withdraw each month? That tells me my goal is that payment. So in order to use our formula, we're going to need to know a couple more values. Notice I'm using the version of the formula that's solved for the payment, and I also in this formula have I and I have N, and so I need to calculate those two things before I start plugging things in. My I, this is my R divided by M, so my I is going to be 0.07 divided by 12. Now if I found the decimal version of this, it would be a decimal that wouldn't terminate. It goes on and on. So don't find the decimal version and then round it. Leave it as 0.07 divided by 12. And my N is my M times my T, so it's going to be 12 times 30, so my M is going to be 360. If I input all these values into the formula, this is what I should have. Now notice when I go to input this into the calculator, since I have more than one thing in the numerator and in the denominator, I need to have parentheses around both of these. So this is how you would do this problem using the formulas. Let's look at how you would do it using the TVM solver. So I've written the different things that I need to have for my TVM solver, and I'm going to go in and figure out what each value is. My N is the number of payments, so this is always my M times my T, so I have 30 years times 12 payments per year, so that's going to be 360. My I is my annual interest rate, so this is going to be 7. My present value, this is the $750,000. My payment, this is my goal. My future value, now they don't specifically give us a future value, but it's assumed here that since they didn't tell us otherwise, that Alonzo's going to have nothing in his account after the 30 years. So my future value is going to be 0. My payment per year and my compounding per year, these are both going to be 12. When we input these into our calculator and solve for the payment, we get that Alonzo is able to withdraw $4,989.77 each month. Let's look at another scenario. When Mei Ling retires, she wants to have an income of $8,000 per month for a period of 30 years, leaving nothing in the account after the 30 years. Her retirement account earns 8% compounded monthly. How much does Mei Ling need to have in the account when she retires? And if Mei Ling plans to work for 25 years, how much does she need to save in the account in order to make sure to have that $8,000 per month when she retires? So let's go back to our picture of the pile of money, or the big bag of money. When Mei Ling is wanting to have a retirement income of $8,000 per month, we're talking about over here on this side over here. We know that the payment, or the amount that she's going to pull out of the account each month, is that $8,000. And so the first thing we're going to need to know is how much does Mei Ling need to have in the account when she retires? Our first goal is to find the present value of this side of the scenario. The second question is about when she's accumulating money. So the second question is about this accumulation side. And our goal is to figure out how much does she need to put into her retirement savings in order to have this side have enough money. Now, we're going to assume that she starts out with nothing, and she's going to end up after her 25 years of savings with some future value. And the key here is that the future value of the accumulation side is going to equal the present value of the withdrawal side. The first thing we're going to do is we're going to solve this side of the scenario. We're going to get this present value, and then we're going to use that to solve this second side of the scenario. Let's look at solving that first side, the withdrawal side of the scenario. I'm going to use the TVM solver to solve this. Again, I'm going to start by listing out my TVM solver values. Our N is our M times our T, and remember, in this scenario, she's going to be pulling money out of the account for 30 years, so we're going to have 30 times 12. Our I is our annual interest rate as a percentage, so my I is going to be 8. The present value, remember from drawing our picture, that was my goal. I needed to know how much does she need to have in the account, how big of a pile of money does she need to have in order to be able to withdraw the $8,000 a month. The payment, that's the $8,000. I'm going to go ahead and make this be negative. It's okay if you don't make it negative, but then your present value will be negative. My future value is 0, and my payments per year and compounding per year are both 12. If you solve for the present value, we end up with $1,090,267.95. If you want to use the formula, this is how our values have to be plugged in. We should end up with the same exact answer using either method. Let's answer the part B of this question. In this question, we want to know she's planning to work for 25 years. How much does she need to save each month in order to be able to pull out the $8,000 a month when she retires? In this question, we're working with the other side of the retirement scenario. The key here is the present value from the first side, from the withdrawal side, has to equal the future value of the accumulation side. Once again, let's write down what our TVM solver values would be. I have my list. This time, instead of using N is 30 years times 12, we're going to have 25 years. So she's only going to be working for 25 years while she was retired for 30 years. My I is the same. It's also 8. My present value, this is the amount that we start in the account. So this, even though I have present value up here, this is from the other side of the scenario. Our present value, we're changing perspectives. Our present value is the amount that we start the account with. So that's going to be assumed to be 0. My payment, this is my goal. I want to know how much does Mei Ling need to put into the account each month in order to be able to retire with the $1 million. My future value is the $1,090,267.95, and the payment per year and compounding per year are both 12. Solve using the TI calculator, and you're going to end up with Mei Ling needs to save $1,146.41 each month. If you want to use the formula, this is how you would input the values. Remember, when you go to enter it into the calculator, you need to have parentheses around the stuff in the numerator, parentheses around the stuff in the denominator. Where did I get the 300? Well, remember, that's my N, and it's going to be 25 times 12 gives you 300. Let's look at a loan scenario. Armand wants to buy a new car that costs $30,000 and pay for it with a 60-month loan at 2.9% compounded monthly. I want to answer 2 questions. What is Armand's monthly car payment, and how much does Armand pay in interest over the life of the loan? The first question, we want to know how much is the car payment. Remember, we can think of this car payment or this loan scenario as the withdrawal side of an annuity. So if we use our TVM solver values, my N, now typically they give us, we have to calculate our N, but they tell us that we're supposed to have a 60-month loan, so that is the total number of payments that we're going to have. So my N is going to be 60. My I is going to be 2.9. My present value, this is the amount of my loan, so this is going to be the $30,000. My payment, this is the goal. This is the thing that I want to find. My future value, the future value is the amount that we want to end up owing after 60 months. And so hopefully that's 0. And my payments per year and my compounding per year, these are both 12. So we're going to input these values in our TVM solver value. We're going to stick our cursor on the payment and solve. We're going to get a payment of $537.73. If you want to use the formula, this is what it's going to look like. Either way, the payment should be the same. Let's answer part B now. Our payment was $537.73, and when we're trying to calculate our interest, well, all we need to do is figure out how much total we actually paid and subtract off the amount that we borrowed. The total that we paid 60 payments. Each payment was the $537.73, and the amount of money that we borrowed was $30,000. So the amount that we ended up paying in interest was $2,263.80. That's it for this video. I hope you found it helpful.